operating system link in here. So you can go to our class page, Teams page, and all the class material and everything is there. So all the announcements, everything will be done in this page. For now, I did not do any announcements yet, but if there are any announcements, we will do that. Anything about the class will be here. So Teams are important for those of you who don't know. Okay, how many people are graduate students in this classroom? Graduate students, just one? Just two? Three? Okay, three. So I don't know what's going on, but I have more than 10 people registered as a graduate student. So the rest of you already know. What did you say that? So are there any Erasmus students? Are you an Erasmus student?
Yes.
How many Erasmus students we have? 1, 2, 3, 4. Okay, so did you use this Teams tool before?
Yes, we use Team.
So you already know about it.
Yes.
So did you join the group yet? Not yet. So you know how to join it?
No.
Well, I just showed you. Just go to our departmental page. Okay. This is our departmental page from the Gebze Technical University. Go to Department of Computer Engineering, and at the, well, maybe go to the English interface. Well, in the English interface, I don't have the announcements. So do you mean announcements? Sorry for that. Okay. So the first one is the links, Teams links for the lectures, for the courses. You click on it, and you get the CSE 312 operating systems. Okay. So you click on it, you register to it, and all the announcements and everything will be there. Okay. Good. So if you have any questions, just see me during the break. I'll try to help you more. Who's your advisor? Advisor, academic advisor? You don't have any academic advisors? So you did not talk to anybody from this department yet? No? Okay, we'll talk to you during the break. Okay, so this is what we do. This is how we are going to do this lecture. And the syllabus, the slides that I am going through is available on those pages. Okay, so current and other useful information, homework announcements, and other kind of announcements will be available on our Teams page. Okay, and I will try to record all the lectures either locally and through the Teams, so all the videos will be available. And as you see, I am broadcasting this lecture online. And if you cannot attend, in person in the class because there is no spot available, then you are supposed to attend it online. Good. Any questions so far? Okay. Can we leave one seat empty between you two guys? You two guys, you cannot sit next to each other. Okay. We have seats available here and there. Okay. So we have to go like this for a little more. It is valid for you guys too. Okay. You like each other so much? Well, you have to wait a few more months. So the required textbook is this one, Operating Systems by Tannenbaum and Boss, okay, by Pearson Publications. It is available at Amazon Bookstore in Turkey for 220 bucks. It is not much, 220 Turkish liras. It's not much actually. It used to be 150 last year, but I mean this year they didn't increase the price that much. Okay, this is the link there too. Just type this name and it will come up, and I think it will be posted in just in a day, so you can receive it in this week actually. And the slides of this book is available in our class page. I made it available. So I didn't bring the book here, but it looks like. Can I open it? Can I open this? Yeah, maybe I can. Can I see this? So this Oh, okay, it is 212. It is better than 220. Yeah, so this is how it looks. Buy this book and never let it go in your life. Okay. Okay, it has very, very nicely written. This guy, this Tannenbaum guy, is a very famous computer scientist. Okay, well, he got old a little bit, but I mean, he has some helpers to write new books. He has some other books in the areas of networking and security and architecture and etc. So he's a good professor, instructor, and a computer scientist actually. So buy this book and read every page one by one, even if I don't cover it. Okay, it's a very nice, very nice, very nice book. So I think the online version of it is available too somewhere if you'd like to buy it. But I strongly, well, these are requirement to buy this book because I'm going to tell you read the chapter, so you should read that chapter. But I strongly suggest you buy this book, either used or new, whatever, and keep it in your library for the rest of your professional life. Okay, so that's the book. Let's go back. Okay, so these are the prerequisites for the course. Okay, you need to know C because our programming assignments homeworks will be in C and some assembly. Okay, for the assembly part, I think our plan for this, I think our uh, plan for this semester is we are going to write our own operating system for the Raspberry Pi environment. So we are going to depart from the MIPS assembly because Raspberry Pi uses ARM-based processors. So you are going to use some ARM assembly, which is not that different from MIPS, but you need to know it. Well, some of the times we are going to use our C compilers to convert our C programs into assembly, ARM assembly, and we are going to talk about it. So, but you need to know about C, and also we know that, okay, as a prerequisite, formal prerequisite, of course, you have to have a passing grade from CSE 102, which is the C programming course, also our computer organization course, CSE 331, which talks about the computer hardware, right? So, I mean, if you didn't pass from these courses, if you didn't get a passing grade from these courses, then you shouldn't be able to take this course. But for some reason, because of a mistake, you are taking it, that doesn't mean that you are going to get a semester or in the middle of the semester. And if they figure out that you did not pass these courses, they will automatically drop this course for you. Okay. For those of you who are the graduate students or our Erasmus friends, if you don't know C programming or if you don't have some background about the computer hardware, then we will talk to you. Maybe it will be okay to take this course for you. Okay. Yeah. So if you do not satisfy these conditions, just talk to me during the break or after the course. Okay, if you are a graduate student or the Erasmus student. If you are one of our undergrad students, then there is no way then you can take this course without passing these two courses. Okay. Any questions? So the homeworks. We are going to use the G++ compilers to compile your homeworks on the provided virtual machine. Okay. So what did I say? We are going to write a operating system for the Raspberry Pi boards, okay? Raspberry Pi computers, which are very, very simple, very, very cheap computers. We did not, I mean, I am not going to ask you to buy one of those computers, but they are very cheap actually. For less than 150 Turkish liras, you can buy very simple Raspberry Pi computer. But I mean, I am not going to ask you to buy one. Maybe you can share one with one of your classmates. So how are you going to write your programs? We are going to use some virtual machines, okay? So virtual Raspberry Pi machine. And so you are supposed to compile your programs on that provided virtual machine. So it doesn't matter what kind of hardware you have. Since it's a virtual machine, it will be all the same for you. So whatever you can compile, we should be able to compile the same thing. Okay. So with the homeworks, we are going to tell you what to do. You are going to strictly follow the homework instructions one by one. This is a very crowded course. Okay, more than 150 people the last time that I checked. So I cannot run different rules for each people, for each person. So we have to follow the same rules. If you deviate from the instructions, homework instructions or other kind of instructions, then well, you will not be in a good situation, and you will put us in a difficult situation too, because it takes time to resolve those kind of problems. Okay. So the grading will be like this. Okay. Okay. Depending on the difficulty levels of the homeworks, depending on the grades that we get from the homework and the final, we can change these numbers up to 5 points maybe. Okay. Maybe midterm will be 35%, maybe homeworks will be 35% or sometimes 40%. So of course, the total is going to be 100%, but approximately it's going to be like that. So as you see, the homeworks and projects are very important. Okay, they are as important as the midterm and the final, and sometimes maybe it will be more important than the final, because I mean, I don't know, maybe it will be 35 and 35 at the end of the semester. Okay, so it is very important to do your homeworks, and we are going to talk about it in a few minutes. Okay, so that's the detail about the grading and the homeworks. Okay, you are not supposed to. Okay, you are expected to submit all of the homeworks. Okay, but if you submit less than 75% of the homeworks, then you are going to get an automatic VF from this course. Okay, VF means that you attended the course. Okay, maybe you attended the exams, but you did not complete the coursework. So VF is worse than FF. FF means that it is a failed. VF means that that person did not complete the course requirements. So if you get a VF, you are considered as not taken this course at all. Okay. So VF is something bad. Don't try to get a grade like this from any course. Okay. And homeworks are due by the described date, which is specified by the homework text. And homeworks will be submitted to the Teams page. And Teams does a very good job of keeping track of how many days and how many hours remain for your submission, etc. Okay, so usually we allow 4 or 5 days of grace period. You are allowed to submit late, up to 4 days maybe, but for each day late, we are going to deduct 10% of your maximum grade. So if you are 1 day late, by 1 day late, I mean usually our deadline is midnight. Okay, if you are 1 minute late, that means you are 1 day late. Okay, after 1 day, your midterm will be, sorry, your homework will be graded over 90, not 100, and then 80, and then 70. So it will go like that. Okay, so we will not accept homework submitted more than 5 days late. Okay, this is a very large crowd again, a very large class, and we know that people are people. There might be some situations that will prevent you from turning your homework on time, or there will be some other problems. So what are we gonna do? Just talk to me. Just send an email. Thank you. Did everybody sign this? Everybody? Do you have your name on this? So if you have a problem, submit it on time, and we will figure out something for you. Okay, if your excuse is excusable. Okay, I have a birthday. My friend has a birthday kind of excuses are not very good excuses. Everybody has a birthday, we know that. And but I mean, some family emergencies, illnesses, COVID-related stuff, etc. Okay, we will usually figure something out. Good. Exams, tentatively 8th week of the semester on Monday. So that means that what? That means open this. Let me open this. Okay. So this is the first week, second, third, fourth, fifth, seventh, and eighth. It looks like it is April 4th. Okay. So tentatively, April 4th is our, let me put in midterm exam. So it is in my, okay, April 4th, okay, at 10:30. Usually, as I said before, well, this is a very large class. I think this is the 5th time I'm taking it. I cannot have enough, I don't have enough space for you to fit in classes like that at 10:30. Usually we do our exams after the usual work time, so it will be maybe around 17:30 or 17. So we will announce it. Okay, so be prepared for this. Okay, you might be a little bit late to home on that day, April 4th. Again, this is tentative. We are going to talk about this, our exam date around 6th week, 7th week. Okay, so just remind me about that when we come to 6th week or 7th week. Okay, the final exam usually we do it on the 2nd week of the exam period, and exam periods are already in academical calendar. So you just look at just attendance is part of the classwork. If you don't attend enough number of classes, you will get a grade of not attended, NA. NA is a grade that is as bad as VF. Okay, VF and NA is worse than FF. Okay, you don't wanna know these grades. The grades that you wanna know are these AAs and BAs. Okay, these are the nice grades. NA and VF and FF are bad grades. Okay, so work for these, not for those. Okay, just let's make this clear at the beginning of the semester. So I expect you to attend all the classes actually, but unfortunately I don't have enough space. So this is what I expect. You attend, there are 14 weeks, lecture weeks in this semester. I like you to attend 14 in-class lectures and 14 online lectures. Okay, Monday or Tuesday, you choose one of them. Okay, and our regulations, our university rules says that if you miss more than 30% of the classes, you will get an A from any course. So that means that you are supposed to attend 70% of this and 70% of this. So what is 70% of 14? Is it 11? Yes. So I expect you attend 11 in-class lectures and 11 online lectures. That's the minimum. Okay, that's the minimum. So don't try to aim for these 11 because we are all humans. There might be some exceptions happening in the future. So try to attend all of them, 14 in class and 14 online. Okay, these are all valid for everybody. Doesn't matter if you are a graduate student or undergrad student. But the university rules also say that if you took this class previously and if you got a grade of FF, okay, that means that you have already satisfied this attendance rule in your previous years, then you don't have to attend the courses. Then be it. That's the rule. So those of you who got an FF previously from this course, these rules are not valid for you. Okay, so you don't have to attend either the in-class lectures or the online lectures. Okay, but then, because it is difficult to get a passing grade from this course or another course without attending it. Especially this year, we have changed the format a little bit. We are switching to a new project format, project framework. Okay. Any questions from our online audience? Any questions from our online audience? So we have 70 people. No? I guess okay.
Hocam katılmayı bekleyen kişiler varmış sanırım derste onayı bekleyen.
By the way, we speak
sorry.
only in English first. So what is the question again?
There are students that waiting for approval to Teams.
Well, let me see if I have it. Yeah, I guess there are many people in there. So they did not read their emails? Yes, regularly, you are supposed to check the Teams page regularly. For those of you who are just attending, you're just joining in the online lecture, I am recording this lecture, so watch this lecture once I am done with it, okay? So I did that. I have, by the way, I have some other, yeah, okay, good. Okay. I know some of you are not students of this course, online people. You are welcome to attend the online lectures. But if you are not a student of this course officially, please don't come to this classroom because, as you know, we don't have enough space already. So let's make it easy for the people who take this class officially. Okay. So if you are not an official student, you are welcome. You are always attend my classes online, ask questions, make contributions. That's fine. We would be happy with it. But please don't attend the classes in person because we don't have enough space. Good. So homework submissions and announcements, as I said before, everything we will be doing it using the Teams page. We are not going to use Moodle system, we are not going to use the system recently started by the university. They call it the course box or ders kutusu. I don't remember the name. So it will be all Teams, okay? It will be all Teams. All the homeworks, all the announcements, all the sharings will be done through the Teams. Okay, good. Honor code, we have honor code, of course. The university has it. You should not misrepresent someone else's work as your own. Do not use work from somebody else. All cases confirmed cheating will be handled accordingly. We have ways of handling it. So don't do any of this stuff. I don't expect anybody doing that kind of stuff, but I have to put this one. So as a rule of thumb, especially when it comes to coding, if you see that two people have similar lines of code, even a single line of code, that might happen out of chance. Okay. Well, I mean, there are some. Everybody can have statements like this. Okay. So I can't do that, but if two people are having many of these kind of lines one after another and they are matching perfectly, then we have to do something about it. If we see such cases, we are not going to ignore it. Okay, we will handle it. So be careful about that. And finally, these are the topics to be covered. I mean, the operating system is very easy to talk about in terms of what we are going to do. It is very easy. We are going to talk about processes, memory, file systems. But talking about processes will take more than a month. Again, another month. Okay. So once you go into the details of it, there are many details of it. And unfortunately, I will not have enough time to talk all the things about all the class material. So I am going to ask you to read the book. Okay. So I think I am going to spend a few weeks about this general introduction first. Then we are going to talk about CPU. This is about CPU, central processing unit. Then we are going to talk about memory, then the file systems, how we store our data on our secondary storage, then how we do input output. Virtualization is becoming, and cloud is becoming very, very important. As I said before, even we are doing our homeworks on a virtual box, right? And then the security and deadlocks. If I have time, I will talk about it. Okay, deadlocks are kind of very classical discussion topics on operating systems. Okay, it is because there are lots of literature about deadlocks, but nobody uses any of these deadlock mechanisms in operating systems. Windows or Linux or any other popular operating systems, they just ignore the deadlocks. So why do we talk about deadlocks? Because it has a very large chapter in all of the operating system box. I don't want to talk about it, but it became part of the operating system curriculum. So I think I will talk about it for a few hours, maybe less. I don't know how much time I have, but I usually operating system talk. I don't like talking about deadlocks. That doesn't mean that deadlocks are not important. It is important for the databases. Okay, there are very nice algorithms for it, but for the operating systems in practice, we don't talk about it. Processes are just very important. Memory management are very important, as you are going to see. File systems are so important. Okay, the history of the operating systems are important. We need to talk about it. It is not because we need to talk about history. It is because history defines what an operating system is. History defines why we are doing this and that. Okay, that's why we are going to talk about that. Good. Okay, so that's the end of the introduction to the course syllabus. And I'm going to start talking about this chapter number 1 from the book, if you don't have any questions. So I am planning to do this 45 minutes of lecture and 15-minute breaks. Usually the university says that 50 minutes of lecture and 10 minutes of break, but due to the COVID conditions, we like to take 15 minutes of break. So that, and during the breaks, please don't sit in the class, just go outside and let some fresh air just in the please open all the windows when you're fresh air for 45 more minutes. So I will stop at 11:15, okay, and we are going to start at 11:30. That's what we are going to do. Good. Questions? Okay, so there are no questions. I will start from my slides are actually from the book. I came a little bit. I took some slides from some other people. I took some slides from some other resources, but all the material come from the book itself. Okay, so if you read the book, you have all the pieces. Okay, so that's the why we study operating systems. Okay, well, I mean there are many reasons why we are studying operating systems. Okay, first, to understand the operating system as a computer engineer. Okay, we don't do anything without some kind of an operating system. But usually, without taking a course, a formal course like this, it is not that easy to understand what exactly operating system does. And you can't achieve this by just reading the books. You need to implement some kind of an operating system to understand it. Okay. For many people, operating systems are just magic. Okay. They don't know what's going on. There is a system called operating system. It's doing something, but most people don't understand. And I'm talking about the system administrators and sometimes computer engineers and computer scientists. They don't know what an operating system is actually exactly. Okay. So the first thing why we are talking about it, we need to understand that's our profession, right? As software people, as computer engineer people, we don't do anything without the operating system. So we need to understand them so that we can write, if we are developing software, we know what kind of things our software are doing actually. Okay, how we are interacting with the operating system. Operating systems are incredibly complex systems. Okay, we are talking about, for the whole operating system, 100 million lines of code. 100 million lines of code. Okay, for the Windows operating system, it is the total operating system is as large as that one. So you don't develop this 100 million lines of code in a single night, or in a year or 2 years or a decade. Okay, it takes lots of time. It takes hundreds of very talented people to develop such complex software systems. Okay, when you write a simple program, actually, for example, our C program, simple hello world program, when you compile that program into assembly, okay, it turns into actually a 1 million lines of code, and that's not an exaggeration. Okay, why? Because this hello world is using lots of libraries, okay, standard libraries, and then those standard libraries are making lots of system calls, operating system calls, and the operating system calls are actually they are implementation of other libraries to print something on the screen. Hundreds of the screens are very complex, and if you put them all together without having this 1 billion lines of code, you cannot achieve even the simplest program. Okay, the simplest program. That's why you say that operating systems are very complex. But well, it is so easy to write a program that prints hello world on the screen, just printf statement, right? That's one of the tasks of the operating system. Make this kind of complicated tasks easy for the end users or the programmers. That's one of the tasks of the operating system. Okay, so we are going to look at that. And then the third reason, okay, operating systems they're just pieces of software. Okay, they know hardware very well, but they are pieces of software. What does that mean? So it's a very good example of very nicely developed, very carefully thought out examples of software. So why not study such systems so that we can take examples of such software? When we are building our software, of course, maybe it won't be as complicated as operating systems, but we can maybe take examples from it. Okay, how we are developing it, how we are dealing with it. Okay, abstractions, we kept talking about abstraction. When you take the C programming course, they talked about the abstraction. You know, there's CSE 241 object-oriented programming. It was all about abstraction, right? So hide the details of underlying software, underlying tools, abstraction. Again, operating system does the same thing in a very large scale. It tries to hide all the details of hardware. Hardware is something complicated, okay? Hardware is something complicated, and in order to able to print this kind of simple statements, simple letters on the screen, you don't have to know about all those complications, so it has to be abstracted away from me. Modularity is another technique that we use in software development, okay? So you don't write your 100 million lines of code in a single function, right? Obviously. You have to modularize it. Okay. In your modules, you should have sub-modules. Under the sub-modules, you should have even more modularity. And most importantly, iteration. Without iteration, humans don't do much development actually. They invent something, okay? They use it for a while. They realize that there are things that are wrong about your implementation, and then they reiterate, okay? So we have many versions of Windows operating system, okay? At every version, we see some new developments, okay? So they say that now we have added this, now we have this, now we have that, okay? So why didn't they add all those features at the beginning? Well, for one thing, maybe they say that, okay, well, USB sticks, they were not available in 1990, so we did not support them. Okay, so that's understandable because the technology wasn't there. But why didn't you add the current, for example, support for the speech-based search on your Windows system? We didn't add it because I mean it was too complicated for that time. Okay, I mean we were dealing with the supporting newly available CPUs then, and we couldn't handle everything. Now we have time, we have resources to add these new capabilities. So iteration is something we experience, we use for any kind of engineering work. You do something, you look at the results, you reiterate, you reiterate and you iterate until infinity. You don't stop. Okay, you don't say that this is perfect now. This is an operating system that is perfect. I am not going to do anything about that. No, you don't say that. So we are going to use all these techniques in a software system that is as complicated as the operating systems. Okay, these are some of the reasons why we are studying operating systems. Okay, so talk about the definition of the operating system. I am not going to give you a like one sentence definition. Instead, we are going to talk about what operating system does instead of the definition itself. So we will talk about mainly two things, 1 and 2. Okay, so we will talk about the software that abstracts the computer hardware through interfaces. Okay, so that's the software. I don't say, do you know how the screens work? This screen, do you know how this screen works? This one? Do you heard about pixels, right? Pixels? How many pixels do I have on the screen? Do you know? Well, usually, how do I get that one? From the I think personalization like that. Maybe the screen adjustments. Do you guys see it? Yeah, here it is. Okay. So I have a matrix of dots, 2000 by 1500. Okay. So there are many dots on my screen. So somebody controls what kind of okay. So this is my screen. There are 1500 rows and there are 2200 columns. Okay, each one is a pixel like that. Okay, for each pixel I have the red, green and blue values, RGB. If my R value is very high and G and B values are very low, then that's a red pixel. Okay, so I see a red dot in there. Okay, I see a red dot in there. So my screen is made up with these kind of matrix values. So in order to print hello world on the screen, somebody has to make this decision of which pixels to assign which values, RGB values. and there's a static screen. If my hello world is scrolling up, okay, then somebody has to refresh my screen so that I am just doing this scrolling up. So who is going to do all that work? Okay, that's something very complicated. Then the bad thing is that my screen is not the only screen that I have to deal with. There are literally thousands of different screen types, and I cannot possibly know the details of all of it. So who makes this isolation between my program and the hardware? It is operating system. So it hides all the messy details of the underlying hardware. I talk about only the screen now, just the display, and we are talking about the details of these cameras. Okay, cameras are very complicated. Again, there are literally hundreds of different types of cameras. And all I do is just plug it in, and I ask my program to get a frame from the camera. Okay, what else? I have my network card. I need to communicate with the wirelessly with the network. Literally, there are hundreds of different types of networks, and I need to communicate with them. There are different hard drives, there are different memory structures, and etc. But as a user, as a programmer, I don't care any of them. All I do is just print this on the screen, get me a package from the web, from the network. Okay, put this on my hard drive in this file, close file, and etc. So all of these simplifications, that's why there are different types of hardware, and they make it easy for me as a programmer to write my program. So all I do is include those IO file, IO headers, and use the printf function. That's what I do. That's what I do. Okay. So they present me a resource abstraction that is easy to use. Also, it does something else too. Okay. It extends or virtualizes the underlying machine. So can anybody tell me what this means? It extends or virtualizes the underlying machine. What is extension of the underlying machine operating system does that? How can I extend? I mean, this machine is a machine. How do I extend it? Just give me your idea. I mean, it doesn't have to be perfectly correct. It doesn't have to be correct. Okay, just tell me something. Who said that? Okay, so that's a very good point. What do you mean by virtual memory?
There is a physical memory, but our operating system extended like a virtual memory there is there. It extends its capabilities, but virtually.
So so why do we use the virtual memory? I mean, what do we gain from this extension? Are you talking? So what are you saying?
Why the physical memory information?
Well, physical memory is very simple actually. I mean, I have the address number 0 and address number FFFFF. Okay, I just address it. Very simple. Let's go back to the virtual memory. Why do we use virtual memory? So you kind of learned about this from 101, right? Do you know how many gigabytes do I have on this computer? I don't. I think I have 8. I have 8 gigabytes. Okay. Currently, I am using. Let me go to my task manager. This is my task manager. Okay. My task manager says that. Okay. I am using 77% of all of my memory out of 8 gigabytes. Okay. And it looks like most of them are being used by this Teams and the OBS. That's what I'm doing. Okay, that's what I'm saying. But if I see what I'm running here, Teams and OBS and Drawboard, this is for Teams, this is for recording my screen. This is for my PDF viewer. This is my Chrome. And for some reason, I am running Edge 2, and OneDrive is running. If I let any of them, okay, their memory requirements are larger than 8 gigabytes. I mean, if you tell them how much memory you need, they say I need 10 gigabytes. They say I need 15 gigabytes, and etc. How many processes do I run? You see this one? How many processes do you think I am running? So it looks like, let's say I have 50 here, maybe 20. One, can I do this? Page, no. 2 pages, 3 pages, 4 pages, 5. It looks like I am running more than 100. It looks like I am running more than 100 processes, and each one needs 8 gigabytes, let's say. I don't have 800 gigabytes of RAM on this computer, but each one thinks that they are using 8 gigabytes of memory. So who is making this possible? Operating system, with the help of hardware, of course, fools each of the processes into thinking they have complete 8 gigabytes of memory available. Okay, so it offers them a virtual memory space. Okay, so each process thinks that they have their own virtual memory space, and that virtual memory space starts from address number 000, and the 0x very large number here, and they say that I am going to keep my array here, my screenshots there, my videos are here. So each one thinks that they have their own memory, but in fact they don't. Okay, so operating system, with the help of hardware, fools them, virtualizes the underlying memory, and we call this virtual memory, as our classmate correctly pointed out. And that's what the operating system does. So that's the time of extending and virtualizing the underlying machine. The same thing happens with the CPU too. I have only I think 4 CPUs on this machine, but I have 100 processors, right? So who is going to do this allocation between the process? Of course, the operating system. But the thing is that each process thinks that, okay, each process thinks that they have their own CPU. Okay, they say that if this is my CPU, what do you have inside your CPU? Tell me something. Tell me the things about your CPUs. What is the most common things that we use in our CPUs when we write programs? When you write programs, what do you use in your CPU? Registers, right? Registers. Register number 1 up to, let's say, for 64-bit computers, I have 64 registers. Each program thinks that they have their own set of 64 registers. And in fact, they don't actually. They are sharing these registers with the other programs, okay? But I virtualize this CPU into something that each process thinks that they have their own CPU and they have their own memory, okay? The same thing with the network adapters, the same thing with the screen, the same thing with the file stuff. So extending and virtualizing the underlying machine is something that we need in our modern computer engineering professional life, and operating system does this for us. And if you don't have this abstraction, then that means what? That means I can run only 1 or 2 programs at the same time, mostly one program, and that will be very, very inefficient for us, right? So if you have an operating system on your machine, that was the first generation computers did. They didn't have an operating system. So what does that mean? They can run only one program at the same time. Okay, and we are going to talk about it. Wow, I ran over so much in a few minutes. Any questions so far? Any questions? I'm going to take a break. Let's be here around 11:40, okay? 15 minutes of break, 11:40. uyuyorsun ya? Uyuma beni dersinde ya. Git arkada uyu. Efendim? Final haftası mı? Final sınavı. Miktar sen de mi yapıyorsun? Yok. Ben finali göstermedim ki. Öyle mi? Tamam o zaman görüşürüz. 9 mu yaptın yani ben?
4'ü yaptınız. Zannedersem bir sonraki hafta olması gerekiyor. Siz 7. hafta yaptınız.
Tamam.
Hocam bir şey soracaktım. Tekler sınavı sonuçlarını
Daha
nereden
okumadım
öğrendin?
yok. Bilmiyorum daha okumadım. Bugün
Sonuçlar
okudum.
nerede yayınlandı?
Bilmiyorum ki. Ben dekana gönderirim oradan söylersin. Oh, yes. So you guys just came in?
Yes, a question because we have already do some C program.
Yeah.
But we don't have the
Computer architecture?
yes, we not done.
You never heard about CPU?
Not really.
Really? Well, I mean, these kind of things happen. I mean, people try to. Well, actually, I mean, it would be very helpful for you to know about that stuff. But so you are second year students or third year students?
Second, yeah.
Second year. But you know C programming, right?
Yes, we.
How about assembly? You know some assembly?
We've done some assembly.
MIPS? You did MIPS or what?
I don't remember the name. Vous vous souvenez de quel assembleur on avait fait?
Contexte 1800
Six,
6800.
Oh, okay, Motorola stuff.
Yes.
Oh, okay. So that's kind of MIPS. That's okay because I mean I am going to talk about a new type of assembly for these guys. These guys learned MIPS, so we are going to do ARM-based programming. So it will be mostly. Well, I mean, I think you will be okay.
Yes.
It will be a little bit difficult, but I mean, you are not going to find in your Erasmus visitation, you're not going to find exact fit for your needs because every department is different.
Mhm.
Either you are going to start from the beginning, which doesn't make much sense, or you're going to take some courses that doesn't fit you very well. But I think it will be okay.
But
It's important that
it will be a C program, but with assembly.
well, some assembly, some C, because operating systems you cannot write it with C programming all the time. It will be some assembly and some C.
Okay.
Okay.
Okay. Nice.
Good. So
Thank
you guys handled everything about where you are staying and that kind of stuff. Are they people helping you?
Yeah. We prepared.
The Erasmus office is helping you.
Yes, the Erasmus office told us to come. So
Okay.
yeah.
So you came from the same university?
Yes, we're all from friends.
From EPITA?
Yes, exactly.
Okay. Yeah, I visited once EPITA.
Yes.
10 years ago. Okay, so any problem? Just let me know. What kind of other courses are you taking?
For now, we are not really sure about with
We have to try a lot of courses and
choose later.
yes, we have to.
We have
We'll start in
5
March.
weeks to have CTS.
Okay.
For now, we are just trying.
Yeah, kind of late. I mean, the course is something like that. I mean,
Yes. We've got.
did they give you any names?
Yes. It's his name.
Professor Göktürk, maybe? Mehmet Göktürk?
Yes, it's him.
So go talk to him and he'll help you.
Okay.
But for any problem, just you can see with you. We just our office is next to each other.
Okay.
Okay, thank you. Okay. See you. Okay, so two main tasks of operating system: abstracting the computer hardware and managing the resources. We are going to talk about this a little bit later. Let's talk more about this abstraction stuff. Okay, or another view of operating system. I think it's the same thing. So this is the first part, and this is the second part. Usually, we show the operating system, position of the operating system in a computer system like that. Okay, this is hardware. There is nothing about software in here. Okay, it is all about CPU, our memory, our network card, our disk, and it is all hardware. On top of the hardware, the closest software that works is the operating system itself. Okay, and operating system acts like an isolation between this complicated hardware and our user programs. Okay, one of our programs is the GNU compiler, or our C shell, or our X11 graphical user interface server, and etc. Whatever you have as a program works on top of the operating system. Again, operating system is a piece of software. Okay, it's not hardware. It's a piece of software. It acts like an isolation mechanism or abstraction mechanism between our programs and the hardware itself. Sometimes people understand this picture in a wrong way, maybe rightly so, but they think that everything GCC does or C shell does goes through the operating system to the hardware, but it is not exactly right actually. let's say I have a program. Let's say, do you guys remember this? Where is my compiler? Network. Okay, I'm back. Do you guys hear me? Do you guys hear me, online people?
Yes, yes.
Yes, we do.
Yes, sir.
I was disconnected a little bit, sorry. So let's go to Compiler Explorer and let's just, for those of you who don't know about this site, it's a very nice way of showing you like this one. Okay, so, and I need to show you, okay, this is just a simple one plus 4. Okay, very simple. Can I make this bigger? No, you don't see it, right? How do I make it bigger? Like that. Yeah, very simple C function, and I am going to see the translated assembly version of it, but I don't remember how. Do you guys remember? How do I see the produced assembly stuff? I add what? No, you add new compiler. Yeah. Okay, so I compiled it using the GCC compiler, very simple compiler, or maybe just for you to understand it better, let me compile it with a MIPS compiler actually. Yeah, this is good. So this is load. What is load? Okay, it already did the addition, right? Maybe I should do this. So this means what? Load, okay, point to register number 2 and add 1 to register number 2 and then put it back to register number 2 and store it back to num, the position of num. So here I am trying to say this. These instructions will run directly on the GPU, the CPU, okay? This is my program. While this program is running, it is trying to execute some instructions. Who is going to execute these instructions? These instructions will be executed by the hardware, by the CPU. Let's say my program name is, this is my operating system again, this is hardware, okay, CPU. And this, while my program is running, not all of my instructions go through the operating system, okay? Operating system lets my program use the CPU directly for these instructions, okay? Because these are harmless instructions. I mean, I cannot do anything bad by doing this stuff. All I am doing is I am loading some data to my registers, I am moving them around, I am adding them, I am multiplying them, and I am putting them back to some memory locations. They all belong to me, okay? So while I am executing all of these instructions, my program is using the hardware directly. So where does the operating system involvement come in? It comes in whenever I try to do something privileged, okay? Something that is special. For example, what? If I like to do some input output to the screen, read some data from the keyboard, then I have to ask the operating system do it for me, okay? Then I have to ask the operating system, say that, okay, read some data from the keyboard, read some data from the network, write something to the screen, okay? In that case, I asked the operating system, and the operating system does that directly on the. Okay, so this layer, don't take this layer as a complete opaque layer. Okay, most of the time, my programs, they access the hardware directly because they are allowed to. Okay, if I am allowed to access the hardware directly, the CPU or the memory or the network buffers and etc., then that will be fine. As a program, if I do something that I shouldn't do, for example, as a program, I am trying to access the parts of the CPU that I am not allowed to, then in that case, operating system will come in and will say that you are trying to execute an illegal instruction, and I am going to stop you. Okay? So that's when the operating system comes in. Operating system comes in when I make a call to system, do this for me, it just starts running. Or if I try to do something stupid, and in that case, operating system will come in and it will stop my process from running. And of course, operating system does this with the help of the hardware. Hardware knows who is the operating system, and hardware knows who is not the operating system. Okay. As a regular program, if I try to do something privileged, okay, such as moving some special instructions for the registers, then the hardware knows that I am not the operating system. I am not allowed to do that, and just lets the operating system know that somebody is doing something stupid. Okay, so that's the way it is actually. Okay, that's the layer. So don't think that I have seen this in many cases in the previous years. Don't think that each of my instructions goes through the operating system's approval. That's not true. Okay, most of the time I am running my program on the CPU itself. From time to time, I ask help from the operating system. Okay. Any questions on this? Okay, so let's go back and we talk about the second part, which is this part. Okay, managing the resources, provide protection and managing the resources. The second thing the operating system does. Can anybody tell me what this providing protection is? Do you have any ideas? What are we protecting? Yes. Memory what? You're saying that somebody is trying to use memory location that doesn't belong to that user, or it's some place that doesn't exist. Okay, yeah. So that's called protection. If I have, let's say, I have, let's call these program number 1 and program number 2. Okay, and hardware, in my hardware, I have the memory location. This is the memory location for program number 1 and memory for program number 2. If P1 is trying to access the memory of the program number 2, then the hardware will let me know, and the operating system will say that that's not going to happen. That's called the protection. Okay, so this is called the memory, and memory is not the only thing that is protected. Okay, for example, the specials in my hardware, there are very important places in my hardware or in my memory, then those places are protected too. And this protection is done so that each of these processes, each of these programs, okay, they can function properly. If somebody is modifying my memory locations, then I cannot function properly. Okay, it's a security is one thing. Other than that, my logic will fall down. Okay, crash if somebody keeps modifying my memory locations. So either accidentally or intentionally. Okay, so somebody has to provide this protection for me. It provides protection and it manages the resources. Management of the resources are important. If this guy wants to use the whole memory for itself all the time, then that's not fair. Okay, what did I show you? I show you that I have more than 100 processes running on this simple, stupid computer, right? If everybody tries to do the same thing, obviously this will not work, okay? So somebody has to provide this management capabilities. Somebody has to provide this management services. So who's going to do that? It is the operating system. Operating system is going to tell each program that, okay, it's now your turn to use the CPU. Use the CPU, but don't use it more than 40 milliseconds, okay? 40 milliseconds. After 40 milliseconds, you need to give me back the CPU. If you don't, I am going to cut you, and I'm going to put you in the wait queue, and I'm going to let some other process use the CPU. So that's called the CPU. The same thing is valid for the memory management. The same thing is valid for the file management, or the network card management, or the screen management, okay? So these are the, again, tasks of the operating system. As you see, operating system is trying to many things at the same time. That's why it is very complicated. That's why it is very, very involved. And the nice thing is that it is so nicely designed and presented. As a programmer, I didn't have to know anything about how the operating system works. As a programmer, I didn't have to know anything about the management stuff or the protection stuff. I wrote my programs, simple programs, okay, thousands of lines of programs. All I did was, okay, I have my memory, I am keeping my data structure here, I am keeping my variables, and my objects are there and there, and I don't care what kind of other programs are running on the same computer, okay? All I care is my computer. So this is all done with the help of the operating system. Without operating system, doing these kinds of videos, because without operating system, you have to handle all of these hardware management, hardware protection, knowing all the things about the hardware and etc. That will be very difficult for me. Okay, good. So that's the second part, management of the resources. Okay, abstracting the software, providing protection and management of the resources. Okay, the same thing again. The same thing again for the abstraction. We talked about this, I guess. I don't have to talk about them over and over and over again. Again, sometimes, okay, this picture helps. Hardware is something that you have learned in 331. Okay, it's your CPU structure, your bus, etc. Operating system is a piece of software that runs on top of hardware. And operating system, CPU has two modes. Okay, basically we can say that CPU has two modes. One is the kernel mode, the other one is the user mode. If you have a program running the CPU in the kernel mode, then you have almost unrestricted access to everything. Okay, you have the owner of the whole thing. Usually only the operating system runs in the kernel mode. Okay, in the kernel mode you can execute any instructions that you like. But our software, our user mode programs, our programs, they run in the user mode of the CPU, and they can only execute limited set of instructions, like the instructions that moves the registers around, modifies the registers, common registers, the memory location, etc. There are some instructions that modify the input-output devices. For example, they say that I want to read the position of the mouse now. It can ask the mouse where your position is, and the mouse will tell you, okay? You don't directly access that memory location or that hardware device directly. That requires a special CPU instruction execution. Only can do that. So as a user program, I ask the operating system to return me the mouse position. Okay, so in that case, I won't care if I am using a touchpad like this, if I am using a wide regular mouse, or the wireless regular mouse, or some like a There are some mouse that use the cameras they look at my face and face detection, and I can do the scrolling by moving my head around. I don't care where the mouse movements are coming from. All I say is that I give me the mouse location to the operating system. Okay. So hardware on top of it, operating system runs in the kernel mode, unrestricted running of the CPU. It can do anything it wants, but our programs run in the user mode. Our programs run in the user mode. We need to ask the operating system to do something privileged, such as reading from the keyboard or writing to the screen, or reading from the file. Okay, but everything is in software here. Okay, either kernel mode or user mode, doesn't matter. Everything is in the software. When a computer boots up, it immediately goes into the kernel mode. Okay, and it knows the operating system. Okay, the operating system sits in a special place on our hard disk. Okay, so that program becomes the operating system, and it starts managing all the rest of the stuff. Okay, and the operating system says that, okay, I initialize this computer. Now I'm going to let these user programs run their programs on the CPU. So it chooses one of them. You run, but not more than 40 milliseconds. After this one is done, and it says that you run, then it takes this turn one by one. So operating system keeps coming back and taking the CPU and doing some housekeeping and letting the other stuff run over and over again. It goes until the computer is shut down. Okay, so it is always active. It is always trying to do something useful between these programs. Each program thinks that they have their own computer, but if they don't, operating system knows. Okay, nice abstracted way of doing stuff in our modern computer systems. Okay, so we talked about the management of the resources. Processors, I have, most of the time, we assume that we have a single CPU. It has to be shared between the processes. I have the memory, large amount of memory, but it is limited. We have the timers. Timers are important. What's a timer? Timer is this. What did I say? Operating system says that, okay, it is your turn to run now. Okay. Operating system tells this web browser that it's now your turn to run. Okay, for 40 milliseconds. And this web browser starts running. And after 40 milliseconds, operating system has to come in. Okay, it has to say that you are done. I'm going to cut you now. I'm going to put you in a wait. But how does the operating system come back? Because operating system is just a program, and this program is using the CPU. In order for the operating system to say something, it has to use the CPU. It's a program, right? How does the operating system come back in?
With the help of hardware.
With the help of hardware. What do you mean? Yes, and there has to be an interrupt, right? You guys remember interrupts? There's timers every 40. When the interrupt happens, somebody has to handle that interrupt. Who is going to handle it? Operating system. How do you know that? Because the operating system sets up all the interrupts at the beginning of the computer boot up. Okay? Operating system says that if the timer interrupt happens, okay, I'm going to handle it. While this program is running, a timer interrupt happens after 40 milliseconds, and operating system takes over the CPU, and he say that, okay, I have seen that web browser has been running for the last 40 milliseconds. Then I'm going to switch to this email reader. It's now going to use it. Okay. Do I have anything to do in the meanwhile, operating system? If there are other things to do in the meanwhile, operating system will do that, and it will let this email reader do its job for 40 milliseconds. Okay. That's what's going to happen. If this web browser before this 40 millisecond time, okay, if that web browser asks the operating system to do something, for example, this web browser say that, okay, it has been 10 milliseconds. I am running this, but I need this data from the disk. Operating system, please bring that data from the disk, okay? Now operating system takes the CPU again. It says that I am going to load this data. This will take 300 milliseconds. Okay, that's going to be very, very long time. So what am I going to do? Web browser, you wait somewhere. While I am getting your data from the disk, I am going to let this email reader use the CPU and the system resources. Okay, so in this case, without the timer, operating system took over. Okay, there are basically two cases. One is the timer, okay, happening. So the operating system takes the CPU, control of the CPU. The other one is these processes voluntarily, they say that I need this from you. Then the operating system does its job. Okay, so we are going to talk about these more detail when we talk about the processes and the threads. Okay, so this has to be done. I mean, what are we doing here? So operating system is managing these. Okay, operating system is managing these resources, CPU resource, memory resource, disk resource, and etc. And the most important resource to manage is the CPU. Okay, that's why we need to abstract away the details of CPU. That's why the chapter number 2 is CPU. Okay, we are going to talk about the CPU abstraction. And our abstraction idea for the CPU is the processes and the threads. And we will talk a lot in detail about, we will talk about the processes and threads a lot more in detail. So I was talking about the timers. Timers are important. They are pieces of hardware. They are programmable. An operating system tells the timer that every 40 milliseconds, okay, make an interrupt. I can program it to be 50 milliseconds or 100 milliseconds, but only the operating system has the privilege to program these timers. As a regular programmer, I cannot do the timer programming, the regular timer programming myself. Of course, I can use the timers with the operating system. For example, I can say this. You know this command in C, sleep? This function sleep? This function sleep says that, okay, I am going to sleep for 100 milliseconds. Okay, what does that mean? Okay, the sleep is handled by the operating system. Operating system says that, okay, I'm going to put this process into wait queue for 100 milliseconds. But how am I going to know that 100 milliseconds passed? I think it's one of these timers. Okay, after 100 milliseconds, a timer interrupt happens, and operating system handles it, and you say that, okay, this one is for this process. Now it is time for that process to wake up. So as a regular program, I can program these timers, but again, I am not programming directly. I am programming it with the help of the operating system. And we are going to talk about these timers when we talk about the input-output chapter. Okay, timers are important. And the other stuff, for example, the disks, our mice, network interfaces, printers, they have all their own ways of running, and operating system knows about them. But usually I don't care, okay? All I care is I just say sleep, that's it. I know that after 100 milliseconds, I will continue, and I don't care how it is done. Okay, and management resources also the between the processes, processes between the multiple users and the programs to share resources and coordinating of the sharing. Good. Okay, so let's talk about this resource management in terms of how we are doing it. We do this sharing between the process users in two ways: in time sharing and in space sharing. CPU is done in time sharing. Okay. I cannot divide CPU into two. One half is yours, the other half is mine. I can't do that, okay? That's not meaningful. But I can CPU in terms of time, okay? I have 5 processes, and this is just 200 milliseconds, and I am going to say P1 is going to use 50 milliseconds, P2, P3, P4, and P5, and back to P1 again, okay? So this is time-wise multiplexing, time-wise sharing of the resource, CPU, okay? For the memory, I have to do it in space, okay? I have this much memory. I am going to divide it into 4. This is the space for process number 1, process number 2, process number 3, and process number 4. So I divided my memory in space into 4. Okay? So, but it takes more than just making this division, making this sharing just as simple as this. Sometimes P1 is more important than P5. Okay? Sometimes we say that if P1 is running, let it run. If P1 is not running, then in that case, P5 can run. Priorities, those are important. Sometimes we can say that P1 should use more memory than P4 because it needs more memory space. So it's all done with the operating system. Okay. Issues of fairness. I have to be fair between the users and the processes. I have to be careful about the protection and security. Okay. And these will come into play and we will talk about them in detail in the coming chapters. Whenever we talk about CPU sharing, fairness protection will come into play. Whenever we talk about memory sharing, again, fairness protection will come into play. Whenever we talk about file sharing, for example, we will talk about these. And of course, efficiency. I mean, to be fair, you cannot have an operating system that is very, very inefficient. Okay? What did we say? Operating system is a piece of software, right? If the operating system is too heavy, then it is using lots of memory and lots of CPU, then I don't have anything left for my programs, right? I am not using this computer to use an operating system. I am using this computer to make this projection, to make my streaming over the internet, and what, and do word processing and etc. I am not using this computer to run an operating system. If I keep 50% of all the resources to run the operating system, then that's not a very successful operating system. It might be fair, it might be protection-wise very good, but that wouldn't be a very good operating system. Sometimes you have to make some compromises, okay? And we will talk about those again later with the coming chapters. Again, it's a program, it has to be optimized. Okay, good. Any questions so far? Right? So when we say operating system, actually, there are 2 views of it, and we are going to use one of them. Wide view is when you say Windows as an operating system, Windows, it includes about Windows, including, for example, Windows has what? Backup system, right? When you say the Windows, just take a backup of my data to the network, OneDrive, and etc. Or when you say Linux, that I am going to use this Linux system with this graphical interface, etc. So when you view the operating system like this, okay, you talk about your system programs, system libraries, servers, shells, GUI, and etc. Okay, all the things that come with when you buy Windows. Okay, you pay $200, and they give you 10 gigabytes of data. Sometimes you call that 10 gigabytes of data, installable data, as your wide view operating system. But narrow definition, we say that operating system is the piece of software that runs in kernel mode. Remember the kernel mode? Kernel mode is the privileged mode that can do anything that it wants. Okay? Sometimes, for example, in this case, let me raise these. Okay? C shell, part of the Linux operating system. Okay? X11 server, the graphical user interface server, is part of the operating system, but the C shell on X11, they don't have to run in the kernel mode. Okay? Whenever they try to do something, they have to draw a window on the screen. They ask the operating system kernel part to do it. Okay? So they run in the user mode, not in the kernel mode. Although they are considered part of the operating system, they don't have to run in the kernel mode. So actually, in our case now, okay, the narrow definition of the operating system, if some piece of code doesn't run in the kernel mode, we don't consider it as a part of the operating system for us. Okay, so in this course of operating system, we usually mean the narrow definition of the operating system. Whether the kernel mode in the privileged mode, whatever software that runs in kernel mode, they can do whatever they want. We call that piece of code an operating system. But for most of the people, okay, when you say Windows or Linux or Mac OS, okay, they say that the whole software that comes with the computer, maybe. So keep this in mind when in this course. From this point on, whatever runs in the kernel mode, it is operating system. Okay, that doesn't mean that other parts we will not look at them. Of course, we are going to look at them, because for some operating system they say that keep the kernel part of the operating system very, very small. Okay, don't write. Okay, remember this. Remember, Windows operating system has like 100 million lines of code. 100 million lines of code. Maybe I don't know the exact numbers. Maybe 10 million lines of code runs in the kernel mode. The rest runs in the user mode. Okay, so very small part of it in the kernel mode, and large part in the user mode. And people say that let's make this even smaller. Okay, some operating system, they have maybe 10,000 lines of code running in the kernel. The rest of them is in the user mode. Okay, why is this? We are going to talk about it later again. You like to keep kernel small. It okay, so it is 15 past 12, and I think I'm going to stop at this point. Tomorrow morning at 10:30, we will continue talking about this. So please read chapter number 1, especially the history of the operating system. Watch videos about it. Okay, watch videos about the history of the computers and the operating system. And the better yet, read your book again, CSE 101. Remember, it has a very nice section of about the history of the computers. And history of the computers and the history of the operating systems are exactly the same, actually. But we are going to look at it in terms of the view of the operating system. Okay, that's it for today. I'll see you tomorrow.